Okay, Luis, I think 4 o'clock we can just kick start. Okay, everybody, welcome to the last lecture in this series. So I think today probably Luis will cover more special topics on the lattice and so on, actually. Okay. So Luis, please go ahead. Yeah.
Yes. So in the lecture of yesterday, we started our discussion of atoms in optical lattices. So we introduced the idea of what an optical lattice is and the important concept of Banach function. Then we discussed why the idea of BEC and this type of GP analysis is not generally applicable when you have atoms in optical lattices, and because basically the system becomes incoherent. And you have to apply other formalities. So we projected, so basically working always in the lowest band, we projected the Hamiltonian into the lowest band binary functions basis, and we derived the Bose-Haber model and found the ground states of the Bose-Haber model using this mean field decoupling that I was discussing yesterday, and found that there are two ground state phases, which are the mode insulator and the superfluid transition, which stem actually from the interplay between interactions, which tend to localize, and hoping, which tends to delocalize. You have this interplay between the two things. So let me now share my screen. So this is, as I say, what we were covering yesterday. So what I would like to discuss today is first, so yesterday we were discussing about these Haber models. Now I will discuss a little bit about spin models. So how to simulate spin models with atoms in optical lattices. And then I will cover a wide range of topics, which I will cover very superficially, but just to give you a quick browse of the different possibilities that you have there. I call it here control possibilities in optical lattices, because this is, I will base this discussion on the possibilities and the parameters that you can control, but I will also discuss which kind of physics you can study from this control. So let's go now to the spin models. And so yesterday we discussed the Bose-Haber model. So we had bosons in an optical lattice. Today we will start our discussion with the fermionic counterpart of these Bose-Haber models, which is the so-called Fermi-Haber model. Yes, so this Fermi-Haber model, in which we have actually two components. So we will have, let me just already make this a sketch here. So we have a lattice, and then we have two different types of fermions. Blue fermions, let's say, and red fermions, let's say. These blue fermions and the red fermions can hop to nearest neighbors. And let's assume that both can hop with the same hopping. Is not necessary, but let's just assume that this is the case. This is nearest neighbors. This is what it means, these brackets. And then now I will call this S, which is this color. And instead of calling it blue and red, I will call it up and down. So this degree of freedom, yes, I will call it the spin degree of freedom. It's not necessarily an actual spin, it's what we could call, it could be just a pseudo spin. It could be even two different fermions, fermionic components. So internal states of an atom, for example. So these are the fermionic operators for the spins in the S component, in the side J, for example. And now we have, so this is the part of the hopping, and then we will have the part of the interaction. So if we have a blue particle and a red particle in the same place, then they interact with a given interaction U. Yes. Yes. So this is the Fermi-Haber Hamiltonian. We have hopping and we have interactions. Now, note that in the tight-binding regime, we can't have two fermions of the same component living in the same place. So this is because we are assuming that we are always in the lowest band. Yes, we have just
Luis, 1 second. I think your battery can showing 17 degree. I don't know, 17%. The iPad battery. Your power is connected.
Oh, so, yes.
Yeah.
Sure. Thank you.
Yeah.
Thank you. Okay, so we can't have two fermions of the same component living in the same place, in the same site, because we are always in one band. And moreover, I mean, single component fermions actually don't interact via S-wave scattering. This is because of all these things, is because of the Pauli exclusion principle. So this is a big difference with respect to the case of bosons. And this will be important for at some point in our discussion. So which kind of phases we can have here? Okay, the first phase is the phase which is well known from solid state physics, which is the band insulator. The band insulator. This is when you have two particles per site at every site. Yes. So this means that the band is completely filled. And if you just have one band, this is an insulator. You will need a second band in order to have some conduction, some metallic state. Yes. So this is the idea of an insulator, traditional idea of the insulator. Then there is, and this insulator does not have to do with interactions. It has just to do with the statistics, with the fermionic statistics. Then there is the same idea of Mott insulator. So band insulator is with two particles per site. Mott insulator is with one particle per site. Yes. There's one fermion of whatever spin, in principle, and we will discuss the spin degree of freedom in a moment, per site. So as for the bosonic case, this occurs because the strong on-site repulsion overcomes the hopping and then makes unfavorable that the particles are, let's say, metallic, itinerant. And then, of course, when the kinetic energy dominates, as for the, similar to the case of boson, when the kinetic energy dominates, there is the metallic state. Yes. So this is, as I say, when U over T dominates. And this is when U over T, when U dominates. So put U dominates. And this is when T dominates, when the mobility dominates. And so we have these three phases, and in particular, we have this Mott insulator to metal transition, which is it plays a similar role to the Mott insulator to superfluid transition that we had before in the case of bosons. Yes, this was observed. So if for bosons, this was observed in 2002. For bosons, this took for fermions, this took a much longer time. So the first experiment on Mott metal transition in fermions is actually of 2008, which was performed by Immanuel Bloch's group and by Tilman Esslinger's group. So Immanuel Bloch at the time I think he was still in Mainz, and Tilman Esslinger at ETH Zurich. So these are the phases, right? And now we will concentrate in this Mott insulator phase with one particle per site, because contrary to the case of boson, yes, here there is an additional degree of freedom, which is the spin degree of freedom. Because what I told you is that the Mott insulator, there is one particle in principle for whatever spin per site. But the question is, what is going to be the spin texture? So how is going to look the spin degree of freedom in this system? Yes. So we are going to focus, as they say in the case. So we are going to have a look to the spin. Yes, degree of freedom, and we are going to focus in this limit, U over T much larger than 1. So we are going to do perturbation theory in T over U. We will have one particle per site, Yes, so we are in the Mott regime. So let's see what happens with the spin distribution. In order to see this, we have to introduce an important idea, which is the idea of super exchange, also called the Anderson super exchange. Yes, super exchange. And the super exchange idea is very simple. Suppose that you have two sides, which we will call the side 1 and the side 2. And here we can have we have one particle per side, but we don't know the color of this particle in principle, right? And the Hamiltonian of this system is composed of two parts. One part is given by the interaction, and the other part is given by the hopping, which I will put. It's just the associated part of the Fermi-Hubbard model. See, we will put it 1, and this is the spin. I will sum just over the spin. C1s, C2s, and the complex conjugated C2s, C1s. Yes. So this is the hopping. Now H0 is our 0 order part, and H1 is the first order, is this perturbation that we have on top of it. So this part of here is going to be the largest energy. Yes. And this part is going to be the perturbation. So if we consider just the H0 and we look for the ground states here, it is clear that we have 4 degenerate states if we consider all possible spin configurations. So we may have that one is up and the other is up. So we have like this. We have down, down. We can have up, down, or we can have down, up. Yes. So we have all these possible configurations, and all these possible configurations have an energy 0 in what concerns H0, because they don't have double occupancies. In the moment in which you have double occupancies, then you have a problem. Yes. But all this, I mean, a problem in the sense that you have a large energy. So all these 4 states are degenerate with an energy 0 in what concerns H0. But now let's do perturbation theory. Yes. So we are going to see what happens with H1. And with H1, you may have now the following possibilities, for example. You may have that, let's suppose that this is up and this is down, right? Now you apply H1. And now you can end, for example, into this configuration. So 2 particles in one side, nothing in the right side. And then you come to this configuration. Yes. Again with H1. You can do the same by H1, but then you go to the other one and then end again in this one. So you have 2 different paths. And these processes are, of course, based on this double occupation, virtual double occupation in these middle states, yes, in here. And this is what is called a super exchange. Yes, you get an exchange up, down into down, up. This is what is called a super exchange because it's mediated by these intermediate states. So if one applies second order perturbation theory and one pays attention to the anti-commutation rules, it's important here, the anti-commutation rules when one does the math, then one gets the following matrix elements in second order, right? So what is the probability that you have this super exchange? This is given by this matrix element. This amplitude is minus 2t squared over u. You do the math with the up and down, and going into up, down, so down, up into up, down into down, up, right? And you will get again minus 2t squared over u. And then you have also the self energies. So these diagonal terms, which are the same but without a minus sign. Yes, these are the self-energies. Okay, so these are the result of the second order processes, but note that there are paths which are blocked by the Pauli exclusion principle. For example, if I have an up and an up, yes, this, I can't have this even virtual hop here. This is not possible. And the same is of course true if I have down and down. This is again not possible, right? So if I apply H1 on these states, I get, strictly speaking, 0, right? So if now I summarize all these things, I get the second order term, which is this minus 2t squared over u. And now I can have up, down, down, up. Minus down, up, up, down, plus up, down, plus down, up, down, up. And now I should get something like this. So, okay. So now the next step in this calculation is that I just simply add here a constant term. Yes, adding a constant term in the energy makes nothing. Yes, this is a gauge, right? So I add a constant energy. So which is of this form, t squared over u. And the identity matrix, so it's up, 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 plus down, 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 plus up, down, down, plus down, up, down, up. Yes, so I add this constant is just, in this basis, just the identity matrix. So this makes nothing. And when I add these two things together, I get something like this, if I did everything correctly. Oh. Down, down. Oops, there we go. Down, down. Minus up, down, minus down, up, down, up. Okay. And this in terms of the creation and annihilation operators of the spins is something of the following form. You take the side 1, up, dagger, 1 down, C2 down, C2 up, plus C1 down, C1 up, C2 up, C2 down. Yes, so this is after this term, plus t squared over u of this term, C1 up, C1 up, minus C2, C1 down, sorry, 1 down, C1 down, C2 up, C2 up, minus C2 down, C2 down, down. And now, and this is the key point, we will introduce the spin operators. So this is SI plus, which is basically flipping the spin of the side I. It's going from down to up. Yes, it destroys down, creates up. So this is a flip of the spin upwards. SI minus is the opposite. Ci down, Ci up, yes? And then we can introduce the Z component of the spin, which is 1/2, which is an effective spin 1/2. Sorry. Which is Ci up, Ci up, minus Ci down, Ci down. Yes, this is the spin 1/2. So I basically count how many ups minus how many downs, and I multiply by 1/2, and this is a number which goes from 1/2 to minus 1/2. Yes, which is the spin. Then this means that I can now write this part of the Hamiltonian in this form. S1 plus S2 minus plus S1 minus S2 plus 4t squared over U S1z S2z. And now you use the definition of the spin operators in quantum mechanics. So S1 plus S2 minus plus S1 minus S2 plus is twice S1x S2x plus S1y S2y. Yes. So you use now the x and y component of the spin operators, spin 1/2 operators, and then you can finally write this second the second order Hamiltonian in this form. So this means that by using second order perturbation theory, which is what I was doing here, by using second order perturbation theory on top of the Mott insulator, then I see that the spin degree of freedom, not the density degree of freedom, which is just dead, is this Mott insulator with 1, 1, 1 particle, but the spin degree of freedom is actually governed by this Hamiltonian, which is nothing else than an antiferromagnetic, isotropic antiferromagnetic Heisenberg Hamiltonian. It's an antiferromagnetic Heisenberg Hamiltonian. It's antiferromagnetic because this part of here, this prefactor, is positive. So this means that the spins tend to align anti-parallel to each other. Yes. So this, which we have just discussed for two sides, can be easily generalized for a multi-site system with nearest neighbor hopping. And then you get basically exactly the same, but now with 4t squared over u SISJ. So basically you can, for many sides, you get just h spin, which is 4t squared over u sum in ij, which are nearest neighbors of Si times Sj. So this is the now for many sides. Yes, many sides. Okay, so now we see that if we are deeply inside of this Mott insulator regime, then the spin physics is given by this Heisenberg antiferromagnet. It's kind of very interesting because this means that we are actually simulating with this an antiferromagnet. Now, it is instructive to see what happens if instead of fermions, you had two component bosons. So basically, we could have exactly this Hamiltonian of here, exactly this Hamiltonian, but now instead of bosons, we had fermions, right? Yes, and assuming that we can have more than 2 bosons per site. Yes. So if we assume that we cannot have more than 2 bosons per site, then you will have the following thing. So for what happens for the case of bosons? Let's see now. For the case of bosons, of course, the main difference is that bosons have no exclusion principle. So this means that, for example, this type of process is, which before it was forbidden, yes, now is possible. So we have this type, these self energies given by this type of processes where this is H1. This was before forbidden. So if you do the math, then you will see that for bosons, you get actually that up, up, and down, down is like this. Up, down, up, down, up, down, is down, up, down, up, is with minus, and down, up, up, down, down, up. So this exchange is also with minus 2t squared over u. Yes, before it was with a plus for fermions. So if you just do exactly the same as we did before, introduce the spin operators and everything, then you see that this Hamiltonian is now the same as it was for the case of fermions, but with a minus sign. Yes. So we have S1, S2. So we have a minus sign here. For the case of fermions, we had a plus. So we have antiferromagnetic coupling. For the case of bosons, we have a ferromagnetic Heisenberg Hamiltonian. Yes. So the spins then will tend to be parallel. So the spin physics is then radically different for two-component bosons compared to the case of two-component fermions, right? So coming back now to the case of fermions, therefore, for two-component fermions, one expects antiferromagnetic ordering of the spins. So experimentally, this took quite some time. The reason for this is because the temperatures, in particular the entropies associated to this antiferromagnetic ordering, are very low. So you needed really, really to have a very, very good control of the experiment and get to very, very low entropies in your system to observe this long-range antiferromagnetism in the system. And this was observed for the first time by the group of Marcus Greiner in Harvard in 2017. So it was like 9 years after the realization of the mode metal transition and 15 years after the realization of the mode insulated to superfluid transition, also by Marcus Greiner and in the group of Emmanuel Bloch. Yes. So this took really, really a long time. Yes. And this opens a lot of very interesting possibilities, which I will not have time to discuss, right? But for example, it is known from condensed matter physics that now I was considering the case in which you have what is called a half field system. So you have all sides have one particle per side, and you have like 50-50% of ups and downs, right? But if you start to dop your system with holes, right, and you cool your system to even, I would say, 1 order of magnitude lower entropy, then you could enter into what has been called the D-wave superconductor, which is one of the main candidates for high TC superconductivity. So it's a kind of very interesting system in which you could study these things, but this has not been yet done. Because I say this is a very challenging thing to reduce entropy to these levels. So this is one of the possible ways of simulating spins. Yes, there are other ways to simulate spin with ultracold atoms. Perhaps the most straightforward way actually to simulate a spin is to use what is called a hardcore boson. Hardcore bosons. Hardcore bosons. Hardcore bosons. So hardcore bosons are bosons in which you cannot have 2 particles in one side. So you have either 0 particles, so nothing in a side, or you have 1 particle, but you forbid to have 2 particles in a given side. And how do you do that? Well, you do that by having a U, an interaction which is very, very, very large. U much, much larger than T in the system. So if you do that, then it is so energetically costly to have double occupancies that de facto you eliminate this possibility from the Hamiltonian. And then you just have a Fermi, a Bose-Haber Hamiltonian, but now simple. Have something like this: Bi dagger Bj, and then let's write the chemical potential also. And as I say, there is this double occupancy which is forbidden, which you can write mathematically as saying that Bi dagger square is 0. So this is the hard core constraint. Yes. In that case, you can do the following. You can map occupation into spin. So you can map occupation into spin. So for example, if you have 0 particle in a given site, you will call it the spin up. If you have 1 particle, you will call it the spin down. Yes. So in this way, you map occupation into spin. Formally, this means that you write Si plus is the B operator, Si minus is the B dagger operator, and SIZ is the 1/2 minus the number occupation operator. This is, by the way, what is called the Holstein-Primakov transformation. Primakov transformation, which is a rather general technique to study, for example, spin waves and spin systems in properties of spin systems. This is for the particular case of a spin 1/2 system, where you have just occupation 0 or 1. Yes, it is a more general form of the Holstein-Primakov transformation. And as I say, this Holstein-Primakov transformation is much more general than this discussion that I am doing right now. Yes, so this is just a particular form of the Holstein-Primakov transformation. So if you eliminate just constants, so if you plug this transformation into here and eliminate just constants, which are irrelevant, then you obtain the following Hamiltonian, which is again a spin Hamiltonian. You obtain the following Hamiltonian. Yes, and this Hamiltonian, this part of here, is what is called a ferromagnetic XX Hamiltonian. Ferromagnetic XX Hamiltonian. And this part of here plays the role of a magnetic field. The chemical potential plays the role of a magnetic field. So this is yet another way of simulating a spin model in this type of systems. Yes, you may complicate it, for example, if the you have different particles with different hoppings, for example, you may complicate it even further and get more complicated spin models. But yet there is yet another possibility, which is rather natural, to study spin systems, which is provided by polar lattice gases, so gases which are interacting via dipole-double interactions, or other forms of long-range interactions. But this I will discuss in the last comment that I would like to make in this lecture today. So this is the so there are, as I say, different ways of generating spin Hamiltonians. So let's just summarize this part. So we have started with the Fermi-Haber model, in which we have 2 components in a single band. They may have hopping, they may have interactions if they meet up with down on the same side. And then we have seen that there are 3 phases: the band insulator, the mode insulator, and the metal. Then we have asked ourselves what happens in a mode insulator with the spin. And then we have seen that this is actually given by this super exchange mechanism, in which there is this virtual double occupancies. And then we have seen that this actually leads to an antiferromagnetic coupling of the spins via these virtual hops in second order, which for the case of bosons, it will be a ferromagnetic coupling. Yes. So, and as I say, this long-range antiferromagnetism has been actually observed experimentally. Now we have seen that I have discussed that there are other ways of generating these spin models, like with hardcore bosons, and as I say, with polar lattice clusters, as we will see later. Okay, so we can, if you have some questions, then we can make the questions now, and then I will go on with the last part.
Okay, so anyone questions up to this part? Okay, Luis, if not, we can just go ahead and take all the questions in the end.
Okay.
Yeah.
So what I would like now to discuss in this last part of this lecture, in this lecture series, is I would like to discuss in a very concise way different control possibilities that you have in optical lattices and which kind of interesting physics you can have from them, from these control possibilities. There are two control possibilities that we have been discussing already before and that I will not mention further. One is the control of the interactions using scattering resonances, which is this first resonances I was discussing in the first or in the second lecture. The other possibility is the possibility I discussed yesterday, which is just simply to increase the strength of the lattice to reduce the hopping, right? But then there are other possibilities which actually open a lot of very interesting physics. The first one that I would like to discuss is the lattice geometry. Yes. So let's discuss the control possibilities, right? Possibilities in optical lattices. So as I say, the first point that I want to discuss is the lattice geometry. The lattice geometry. So up to now, we have just considered a cubic lattice. Yeah, so we had this lattice, which had each neighbor had six. Each side had 6 neighbors and so on. But actually, you can realize many other lattice geometries. Many other. Of course, you can have a square lattice in 2D. You can have a 1D lattice. Yes, but these are just the simplest variations of this, right? But you can have very different types of lattices. For example, you can engineer lattices which one could call quasi 1D, so which are the so-called ladder geometries. For example, a square ladder geometry or other ladder geometries. So ladder. You can have triangular lattices. Yes. And so on. So triangular. You can have more complicated lattices like the so-called Kagome lattice. And I am mentioning now lattices which have been actually generated experimentally, right? I will mention now in a second why this Kagome lattice, for example, is so interesting. This is this sort of David star lattice here. You can have graphene-like lattices, so a sort of honeycomb lattice. Yes. And so on. Yes. And much more. You can actually control the lattice geometry to a very high degree by just simply playing with orientations of the lasers and different properties of the interaction between atoms and light. And this opens a lot of possibilities, right? So as I say, all these things have been generated. But you can study, for example, things that you can study using this lattice geometry include magnetic frustration. Magnetic frustration. So, I mean, it is very easy to see why this frustration can happen in some of these ladders. For example, if you put these super exchange models that I was discussing before in, for example, a triangular lattice, and where you have an antiferromagnetic coupling, and you can see that in a triangular plaquette of this triangular ladder, right? And you can have, in this side, you can have spin up. In this side, you can have spin down. But now, since all the couplings are antiferromagnet, then you don't know what you have to put there. This is the idea of the key idea of the magnetic frustration. And this leads to a lot of very interesting for example, ground state phases in antiferromagnets, which are geometrically frustrated like this. Other interesting thing is that is related with the band structure and the topology of the bands, for example. In particular, combined with the idea of synthetic magnetism that I will discuss after this point, right? So you can study bands which have topological properties, topological particular bands that have, for example, what is called a Chern number, which is non-zero, and so on. You can have also deeply connected actually with this is the idea of flat bands. Yes. So, for example, in the Kagome lattice, if you study the Kagome lattice, you will see that the unit cell has actually 3 sides. And this means that you have 3 bands. In the lowest band is actually split into 3 bands. You have a look to how these bands look like in the first brilliant zone. The bands look actually like this. And the important thing is that the upper one is actually flat. This is flat. And for the case of the Kagome band, there are other lattices which have flat bands. But when you have a flat band, this is very interesting because this means that the mobility is basically 0. So this means that the equivalent of the kinetic energy when you are in the flat band is 0, and therefore any interaction leads your transforms your system into a strong interacting system, and you have correlated insulators, for example, and things like that. Also very associated with this is the idea that you can simulate, for example, graphene-like physics. Graphene-like physics, even twisted graphene-like physics. Yes. And then you can have a look also, as I say, in the context of these graphene-like bands, graphene-like lattices to topology, also to, for example, formation of flat bands in twisted Bailey graphene-like lattices and so on. So you have a lot of possibilities, and actually this is a part of research which is kind of active, in particular in what concerns topology and interpreting topology and interactions. So this is the first possibility that I wanted to discuss, just to tell you that there is this possibility to play with the lattice geometry, and actually here the possibilities are very wide, so to say. So there are a lot of possibilities to play with this and with the corresponding physics. The second, which I have already briefly mentioned right now, is the idea of the so-called synthetic gauge fields, or synthetic magnetism, if you want. It's more general than just synthetic magnetism, but basically the idea here is the following. In principle, experiments with ultracold atoms are performed with neutral particles, right? So there's no charge. And since there is no charge, there can't be a direct orbital effect of any external magnetic field. So in other words, there is no Lorentz force, there is no charge, right? But one may mimic the effect of a magnetic field. And this is why it's called synthetic magnetic field, because you can somehow like create it artificially. And this was actually first shown experimentally in the bulk, so I mean without a lattice. But here I will just concentrate on how this is done, or this may be done in lattices. In order to understand what does it mean in the case of lattices to have a magnetic field, let's just consider a particle in a lattice in the presence of a vector potential. So suppose that we have a vector potential A, yes? Let's find what does this mean for a particle in a lattice. Now, in the presence of a vector potential, the Hamiltonian is given by the minimal coupling, yes? So we displace the momentum with the vector potential. And then we will have the lattice. I don't consider interactions here, just consider the lattice. Yes, it's basically a single particle physics here. Now, if I have a look to the hopping term, and I do exactly the same thing that I did when I was evaluating the Bose-Einstein Hamiltonian, if you remember, I was doing something like this. I was taking here the Barnier function in one side. I was putting here the kinetic energy, but here it will be something like this. Yes, with the shift given by the vector potential plus the lattice. And I do it just in one dimension, right? And then I put the neighboring Barnier function. And now here I introduce a gauge transformation. So I just do the following. Yes, I put this transformation. And here I should put the next. So then what I get is something like this. I get EIAXD. Yes, where D is the lattice spacing. I use the same notation. And then I have here, I should put X just something. As if I had no vector potential. And this is just the hoping that we will have without any vector potential. Let's call it T0. So this means that having a vector potential, it amounts to the fact that now my hope is not a real number, but something which has here a phase phi. This phase phi is directly related with the presence of the vector potential because the vector potential is the phase divided by D. So having a complex tunneling, so when I go from a given site to the next site, my particle hops from here to here, but this hop now has a phase, yes? Having this phase is equivalent to having a vector potential in the system, yes? Following this argument that I was mentioning here. And now, as we know, if the curl of the vector potential is different than 0, this curl is the magnetic field. So if this curl is different than 0, then we are able to induce the equivalent of a magnetic field. So we have a synthetic magnetic field. And this has been actually induced experimentally. This may be done in various ways, and it has been actually realized experimentally in different ways. And one of the ways, perhaps the simplest way, and the way which has been mostly used for the generation of magnetic fields, is to use what is called Raman-assisted hopping, right? And this is a very simple idea. Suppose that I take a lattice and I tilt the lattice, for example, in gravity, or I use a constant force. And now my potential looks like this, yes? So there is a tilt. So in addition to my Hubbard Hamiltonian, I add some tilting, which is a tilting term is something like this, yes? So this means that from one side to the next side, there is a energy penalty delta. Yes. Now, if this delta is much larger than the hopping that I may have naturally from one side to the neighboring side, then this means that I simply can neglect a direct hop. But what I can do is to assist this hop using what is called a Raman transition. So you take an excited state here, and then you do a two-color transition. You absorb a photon of one color and emit a photon of another color. Yes. So this photon has an energy omega-1 and momentum k1. And this photon has an energy omega-2 and momentum k2. So if omega-1 minus omega-2 is equal to delta, then this means that I can resonantly pump particles from one side to the neighboring one. But when I do that, my system is getting a kick, yes, which is this k1 minus k2. It absorbs momentum k1 and emits momentum k2. And these two are not necessarily the same. And this is the key point. This is the key point, because it's in this kick, in this absorption, where you may get actually a phase. Yes. And this is actually what is done in the experiment. So for example, suppose that I take a two-dimensional square lattice. This is a plaquette. I will call this the site. So this, let's call this the y direction, and this the x direction. And this I will call the mn site, this one. And this is the, let's say, m+1 n site. This is the mn+1 and this one. And this one is the m+1 n+1 site. Okay? So now I can have this type of Raman-assisted hopping from here to here. Yes. And due to this kick that I have here, this has two, let's say, components in the x direction and in the y direction. Yes. And due to this kick, then one can see that the hopping is actually of this form. Yes. And phi x is delta kx times d, where this is the lattice spacing, and phi y is delta ky d. So this means that now we are putting exactly these phases which are going to act like the vector potential that I was telling to you. So this means that now, if I see what I have in the plaquettes, in this two-dimensional system, so for example, let's say from here to here, I have a phase which is phi x plus phi y. From here to here, I get a phase which is phi x plus 2 phi y. From here to here, I get a phase which is phi x plus 3 phi y. 2 phi x plus 3 phi y. 2 phi x plus 2 phi y. 2 phi x plus phi y, and so on. And now, and then, so this is for the hopping along the x direction. So this is the x direction I told you. For the hopping along the y direction, I will assume that the hopping is just the natural hopping. So there is no tilting along the y direction. So I can really hop here with some given hop, some real hop t along this direction. So here I don't pick up a phase when I hop. Yes. So let's go around a plaquette. Okay, let's go around a plaquette. Let's take, for example, I don't know, this plaquette. Let's start here. When I go from here to here, I pick up a phase which is phi x plus 3 phi y. Let's write it here, phi x plus 3 phi y. When I go from here to here, I pick no phase. When I go from here to here, I pick the negative phase to this one. So I get minus phi x minus 2 phi y. And when I get from here to here, I get no phase. So in total, I am getting a phase phi y. If you make the math, you see that you get the phase phi y in all the plaquettes. So this means that in a plaquette, you get a phase phi y. In the other one, you get a phase phi y, and so on. So if you see which is the vector potential, yes, the vector potential is, apart from a constant, is something of the form phi x x plus phi y y in the x direction. Yes, so this is what we just said, is this phase that we are picking. And if you take the curl of this, you see immediately that this is phi y in the z direction, or proportional to phi y in the z direction. Yes, so this means that you are indeed engineering a vector potential, a magnetic field in the z direction. Indeed, this phase phi y is nothing else than what is called the Aranov-Bohm phase that you get because you are pinning this surface of the plaquette by a magnetic, by this effective magnetic field. So this magnetic field that you can generate here can be actually effectively very, very strong, right? This and actually this significantly distorts the band structure. It can lead to what is called a fractal band structure and something which is called the Hofstadter butterfly. Hofstadter butterfly. Yes. So I recommend you to have a look, for example, on the internet. The Hofstadter butterfly is a beautiful picture of fractal bands and so on. And this you can have in principle in the system because here you can generate a very, very strong magnetic field. The generation of synthetic magnetic fields opens a lot of interesting possibilities, including the study of quantum Hall physics and, as I said before, topological bands, topological systems. So it opens a lot of very interesting physics. Okay, so we have seen now two possibilities. One is the lattice geometry, and the other is the generation of synthetic magnetic fields, and more generally synthetic gauge fields in the system. So here there are a lot of very interesting new developments, which I don't have time to review. But for example, you can have magnetic fields which are not like these ones that I am discussing here, but are, for example, induced by the matter itself, so they are density dependent. You can have the equivalent of dynamical gauge fields, so you can basically mimic at least relatively simple what is called lattice gauge theories. So this is a rather active field, also with some first experiments, promising experiments in this direction with cold gases. Okay. So this is the synthetic magnetism. So let's go now to the third possibility that I wanted to discuss now very briefly, which is the issue of spin-or gases. Yes, so up to now, we have considered either one component systems, for example, in the case of the Bose-Haber Hamiltonian, or two component systems, for example, in the case of the Fermi-Haber Hamiltonian. So in the two component system, this is the equivalent of having a spin 1/2 system. But actually with atoms, you may have a much richer spin degree of freedom, much richer internal degree of freedom with more than two components. You may have three components, you may have four components. And in some systems which have been realized recently, for example, in so-called lanthanides, you may have 22 internal components. So it's really a very, very rich system. And these so-called spin-or gases have attracted the attention of the quantum gases community since many years. Yes, not only in the context of lattice gases, but also more generally in the context of condensates, for example. It has attracted a lot of interest ranging from, I don't know, from nonlinear physics to, for example, applications to quantum metrology. For example, somebody was asking me, I think it was the first day, about the standard quantum limit, and this has been actually, for example, surpassed with spin-or condensates. But the spin-or gases also open a lot of interesting possibility in the context of lattice gases. And this is due to the interplay between internal and external degrees of freedom. So let me now briefly mention 2 points in which this internal degree of freedom leads to interesting physics. On one side, the interactions, let's call it A, the interactions are richer. The interactions are, I would say, much richer. So up to now, we were discussing just the situation in which we have bosons. So boson with boson, we interact with a given scattering length. Or we had two fermions, one spin up and one spin down, and they will also interact with a single scattering length. But if we have spins, if we have a much richer spin structure, yes, then we can have much more complicated spin, much more complicated collisions. For example, we could have particles with a given spin, yes, let's see, a spin S, and therefore the M state, the magnetic state, goes from -S to +S, right? Now, if you have two particles, you can have a particle with a spin M1 colliding with a particle with a spin M2, yes, the two collide. And then you may get particles with a spin M3 and with a spin M4. Yes, for a spin 1/2. So actually, this collision actually, if it is actually mediated by this type of S-wave collisions, it cannot change actually the spin projection because of the symmetry. So it must have that the total spin projection must be preserved, and 1 plus n2 is equal to n3 plus n4. If you have just two identical particles, this is of course boring. If you have two fermions with a spin up and a spin down, this is also boring because up with down just can get you up with down. But if you have, for example, spin 1, right? Let's say spin 1, you can have a spin -1, 0, and 1. And therefore, you can have collisions, for example, of the form 0 with 0, which gives you 1 with -1. Yes, this is what is called a spin changing collision. Spin changing collision. And this type of spin changing collisions result in the very interesting ground state physics and spin dynamics in this type of systems, also in the lattice business. Yes, you may have extend the idea of super exchange to these spinor gases, including the effect of these spin changing collisions. Then you may get more complicated spin Hamiltonians, for example, for the case of spin 1, as I say, adding this effect of spin of super exchange, you may have, for example, Hamiltonians of this form. Let's call it J. So you may have like J1, Si, Sj, but then you may have another term, for example, with Si, Sj square, which comes directly from this these additional terms that you have in the case of spin 1. Yes, and this is the so-called bilinear biquadratic Hamiltonian, which introduces also a lot of very rich physics in the system, a lot of different type of phases in the ground state, for example. So this is one of the reasons why the spinor gases are interesting. Other reason that I would like to mention here is the idea of what is called the synthetic dimension. Synthetic dimension. The idea of synthetic dimension is something very simple. Is to consider the internal degree of freedom as a sort of external degree of freedom. So let me see what I mean with that. Suppose that you have particles in a one-dimensional lattice, right? And here we have three colors. Let's say we have spin -1, a spin 0, and a spin +1, for example. Now you can add, and this is the side J, the side J +1, and the side J +2. So you can now understand this problem as a problem in which you have actually 3 wires, right? Let's do it like this. Yes. 3 wires. And this is this, I will call it the blue wire, the red wire, and the green wire. And this is the J, J +1, J +2, and so on. So now you see that this internal degree of freedom is acting like an effective second dimension, which is this synthetic dimension, right? In this case, the synthetic dimension is relatively small because we have just 3 components. But if you have a system which has much more internal components, then your synthetic dimension can be pretty large. Now, if you now have Raman transitions, for example, that transform your blue into green or green into red, for example, then you induce effective hoppings between these different components. And then you see that you transform your system into an effective square ladder. Yes, where you have, let's say, a real dimension, which is this one, and a synthetic dimension, which is this other one. This has been, for example, used for the study of also of synthetic magnetism. Yes, because you can induce now an effective flux, an effective magnetic field in this synthetic lattice. Yes, and this opens a lot of very interesting possibilities for engineering of models in optical lattices. So this has been, so you can study, as I say, synthetic magnetic fields in ladders and ribbons, or you can study dimensions larger than 3. Yes, because this acts like an effective dimension. So this is also an interesting possibility. Okay, so this is the third thing that I wanted to discuss, these spinor gases, right? Which offers you a richer interaction possibilities, and it offers you the possibility of studying a synthetic dimension. The fourth topic that I wanted to discuss, which is a topic which is very much, it's a hot topic now, is the idea of disorder. Disorder. Optical lattices, as I was mentioning to you yesterday, in contrast to even very pure crystals, provide a pristine periodic potential. So they have neither phonons, nor disclinations, nor defects, and so on. But one may actually create disorder in these systems, and one may create them in a controllable way. There are different ways to do so. Yes, you can take a lattice, right? And then you can overimpose a random optical field, which is, so you can overimpose, for example, speckle light. Speckle, which is this granular light that you have when you impinge with a laser pointer a wall. Then you see these points, right? This is the so-called speckle. So you obtain it when you pass, for example, laser through a diffuser. And this generates this type of random potential. Yes, and basically what this means is that in your Hubbard Hamiltonian, you will have the Hubbard Hamiltonian, for example, the Bose-Hubbard, but then you will have a term of the following form. Yes, where this EI is random and is possibly bound between some given values between minus W and W, where W is just some number, right? Which tells you the strength of the disorder. Yes. So this is the case of random fields. Other possibility is, for example, to take a primary, so this is what I would call real disorder, but then you can have what is called quasi disorder, which has been also studied a lot, which is that you have a lattice, a primary lattice, and then you have a secondary lattice, which is not commensurate with the first lattice. So what this means is that you are going to have your Hubbard Hamiltonian plus something which is not exactly, which has some strength, delta, let's say, it's not strictly speaking random. It's something of this form. So this is this secondary lattice. But if this number of here is an irrational number, right? Then these two lattices are going to be incommensurate with each other. And this is what is called a quasi-disorder system, or if you look at it from the other side, what is called a quasi-periodic system, right? People has been studying this in 1D and also in 2D, where you have the equivalent of a quasi-crystal, for example, with an optical lattice. So disorder is a very interesting topic in quantum physics. There are many reasons for that. Actually, going back to the end of the 50s, when the Nobel Prize winner Philip Anderson introduced the idea of Anderson localization. So this idea is that, and this is something which is well known now, is that in 1D and 2D systems, all single particle eigenstates are localized in presence of an even arbitrarily small disorder. This is the idea of Anderson localization. Anderson localization. This is true for truly disordered systems, not this quasi-disorder. Anderson localization, yes. This is for a non-interacting system, but the interplay between disorder and interactions in many-body quantum systems is a topic which has attracted a lot of interactions in recent years. In particular, in the context of something which has been called the many-body localization problem. Many-body localization problem, MBL. Yes, and this is has attracted a lot of attention because the idea of ergodicity, the idea of thermalization, is on the basis of statistical mechanics. So typically, when you have, you can't think that, okay, if I have an interacting system, then it's going to be a mess at some point, and then I recover ergodicity and I recover basically the statistical mechanics. But this turns out to be a much more complicated problem if one thinks about it. In particular, in the presence of disorder, you may have that your system actually presents what one could call the many-body equivalent of Anderson localization, so the many-body localization. So many-body localization constitutes one of the most active topics in condensed matter physics nowadays, in general, and in quantum gases in particular. And indeed, it's actually, and this is something which is a very recent development, one can have many-body localization both in the presence and in the absence of disorder. So there is many-body localization, like at least physics, in the absence of disorder, just purely due to the interactions. So this is a topic of a lot of interest. So disorder is, again, a possibility which, as I say, is introduced by the possibilities that you can do with an optical lattice, but it also opens a lot of possibilities which can even go beyond, as I say, disorder itself. So the idea of localization is maybe more general than just for disorder systems. And let me finish with the fifth comment that I wanted to make here, which is about polar gases. Polar gases, which is something that I was already mentioning at some point. So up to now, we just considered S-wave interactions. So we just consider interactions that they can describe with a scattering length. Yes. So we had this, you remember when we introduced interactions, we have this interaction potential, which was decaying like 1 over r to the power 6. And we were just substituting it by a pseudo potential, which was this G delta, if you remember. But there is actually a new generation of experiments with particles that interact strongly via other types of interactions, in particular power law interactions, and in particular dipolar interactions. There are other types of experiments with power law interactions, for example, with ions, but let me just focus on the case of polar lattice gases or polar gases. In polar gases, you have, for example, you have either magnetic dipoles or electric dipoles. And magnetic dipoles and electric dipoles have a preferred direction, which is given by the dipole orientation. Yes. So it's not the same that the dipoles interact in this direction or interact, for example, in this direction. So it depends on the angle, right? It depends on this angle. So the dipole-dipole interaction is something of this form, with some d here, 1 minus 3 cosinus squared theta. So this is the dipole-dipole interaction. So this interaction is both anisotropic, whereas this interaction was obviously isotropic, and it is long range. It decays like 1 over r to the power 3 instead of decaying, being basically a contact interaction like it is the case of the typical van der Waals-like interaction. The presence of other forms of interaction, in particular the presence of the dipole-dipole interaction, changes radically the properties of ultracold gases. As I told you in the first lecture or the second lecture, despite of the fact that these gases are extremely dilute, interactions play a very, very important role. Yes. This is true in the weakly interacting regime, and of course, it is very much even more true in the case of strongly interacting systems, for example, in lattices. And therefore, if I change the properties, and I am changing qualitatively the properties, because now it's long range instead of being short range, is anisotropic instead of being isotropic, then this means that I will get a lot of interesting qualitatively new physics when I compare the physics of ultracold gases with and without dipolar interactions. This includes, for example, the BEC physics, not only the polar lattice gases, but also the BEC physics. And some salient novel features include, for example, in the case of the BEC physics, include, for example, the fact that the stability depends on the trap geometry, So it's the geometry dependent stability. Yes, this has been observed experimentally. You can have a roton in the spectrum. So the volume of a spectrum has a roton similar to helium, but due to actually different reasons, right? This has been also observed now very recently in 2018. You may have self-bound dipolar condensates without a trap in 3 dimensions, yes. And this is actually what is called, has been called a droplet, or a dipolar droplet. And these dipolar droplets can form droplet arrays, which form a supersolid. I also mentioned the idea of supersolid at some point in this lecture series. So this is a very, very recent development of the last year or a couple of years. So basically you can have an array, basically a distribution of a dipolar condensate, which possess both off-diagonal and diagonal long-range order. So you have crystalline order and at the same time superfluidity. So in the context of BEC, dipolar BEC, this is still a topic which is very active, and especially in the last couple of years, it has had a lot of breakthroughs. But if I want to focus in the case of lattice physics, the long-range character of the dipolar interaction results in a lot of interesting physics because it provides, so if I go just to lattices here, which is what I wanted to stress now. In the case of lattices, now I don't need to have 2 particles in the same site in order to have them interacting. You remember, in the case of the Bose-Haber model, I needed to have the 2 particles in the same site to have this interaction U. But now I can have 2 particles at different sites, and due to this 1/r³ character, I can have a strong interaction between them at neighboring sites, even beyond neighboring sites. For example, this guy with that guy. Yes. So now I will get strong interactions, and I don't need super exchange actually to have this type of nearest neighbor or next to nearest neighbor interactions. So I don't need super exchange. My Haber Hamiltonian is actually directly something like this. So if I do the same formalism that I did for the case of the Bose-Haber Hamiltonian with just contact interactions, I can get hop-in, I will get on-site interactions, but then I can have other interactions. Yes, which will decay like something to the power 3, and I and j. In principle, I can have also some anisotropy here, but let's suppose that I have just particles, let's say, in a square lattice, and the dipole is like that. Then the anisotropy disappears, and I just have something like 1/r to the power 3. So this is the new thing. This we didn't have before. Yes, and this introduces a lot of interesting physics in these systems. Yes, this introduces a wealth of noble ground state phases, so which go well beyond just the multi-insulator and the superfluid. You can have crystals, for example. For example, you can have in 2D, you can have things like this as the ground state, like a sort of checkerboard, for example, patterns. You may have super solids, which present, for example, this type of crystalline order, and at the same time they still remain super fluid. This is what you call a lattice supersolid. You may have other types of phases, which I don't have time to comment. Also, since super exchange is not needed, these systems are very well suited for the simulation of quantum magnetism. And actually, this is actually something that has been already at least started to be explored in experiments. Yes. So you may have, for example, a site where you have a given spin, yes, and another with another spin. Let's call it with 2 different colors, right? So there are 2 different spin components, and now due to the induced dipole-dipole interaction, then you can have a spin physics. Yes, you can have SI terms and this sort of things, right? And now you don't need a super exchange. So this can be much stronger than the super exchange. You remember the super exchange was going like t squared over u, which is very small. In here, it's just purely due to the mediated, to the dipole-double interaction. This may be very strong. So there are first experiments which have been performed in spin models. There have been very first experiments very recently, a few years ago, on the observation of at least nearest neighbor dipolar interactions. But it is fair to say that the polar lattice gases are at this time, in what concerns experiments, in the very infancy, I would say. And there are a lot of very interesting questions associated to the, also in particular to the dynamics in these types of systems. Okay, so with this, I would like to finish. So we have the, we have seen a lot of different possibilities that you have in optical lattices. We have said that you can control the lattice geometry. You can study magnetic frustration, topology, flat bands, graphene-like physics. You can induce synthetic gauge fields and study, as I say, topology, but also lattice gauge theories and this sort of stuff. You can study spinor gases and induce more involved spin models and even add a synthetic dimension. You can induce disorder or quasi disorder and study localization and interplay between disorder and interactions, which is a very active field, as I say. And you can add other types of interaction, as I say, polar gases is one of them. There are other systems like ions, where you have, for example, Coulomb-like interactions or other forms of interactions, power law interactions, which lead to also a lot of possibilities, in particular in the concept of lattice gases, both for the ground state properties and very particularly also for the dynamics. Okay, so with this, I would like to finish, just to give you this quick browse. Okay, thank you.
Thank you, Luis, for this wonderful expedition of different research topics in cold atoms. And probably we can take now questions. And there are a couple of questions already in the chat box, but if there is somebody want to ask directly the question, please go ahead and then we will go through the questions in the chat box.
Yeah,
okay.
One question. So quasi disordered thing, when you discuss this kind of cosine kind of profile, so one actually previously you also discussed the harmonic profile on top of Bose-Einstein model. And then you say
sorry, I don't understand. I don't understand your question. Sorry, can you repeat?
No. My question is on quasi disordered thing. So,
yes.
So on the insulator on the top of the lattice, we have another secondary profile, right? So previously you also discussed something like Bose-Einstein model on top of the harmonic kind of profile, and there you say that chemical potential will be replaced by the local chemical potential kind of.
Yes.
Right. So here we can do similar kind of thing, or the quasi disorder, because the chemical potential and it has also similarly like local kind of thing if we replace it and yes. Do the
yes,
so
yes, the local chemical, you can understand this as a local chemical potential. The local chemical potential has this disorder or quasi disorder. In the case of the harmonic trap, it was this type of harmonic confinement. And when we were doing the local density approximation in order to start to have this wedding cake structure, for example, we were assuming that this potential was changing very slowly from side to side. Yes, this is the basis of using the local density approximation. Now here, this is different, right? It may change abruptly from side to side, like for example, in this for these speckles, for example. But it will change also rather abruptly from one side to side in these quasi-periodic systems. This has still some correlations which you do not have in principle here. And this actually makes that the localization properties in quasi-disorder are different than the localization properties in disorder. For example, in one-dimensional disorder systems, truly disorder systems, as I say, there is Anderson localization for any strength of the disorder, for any value of this W that I am here. But in the case of quasi-disorder, you need to have a critical strength of this quasi-disorder in order to have localization.
But Anderson localization used it for non-interacting system 1D and 2D for any strength of disorder, it will be localized. For Bose-Einstein model, you also have a interaction. So with interaction also 1D, it will be like localized for any strength of disorder. You are seeing that.
The presence of interactions actually make your system initially. So there is an interesting interplay between localization and disorder actually, because when you increase at small interactions, right, the interactions actually decrease localization. Yes, but when the interactions are strong, you increase again localization. So it's a sort of non-trivial interplay.
Like asymptotic freedom in QCD kind of thing, or
well, it's not really like that. No, it is actually the fact that when you have interactions, basically, you can see this in a relatively simple way in the following form: the non-interacting solutions, the wave functions, are basically localized islands. When you introduce interactions, yes, and you start to increase interactions, these islands get broader, right? Because of the effect of repulsion, basically. I am talking about repulsive interactions, right? And these actually may destroy localization, because may link these islands. But if the interaction is too strong, then you start to have effects based on this basically the mode physics. Right?
Okay, then again the localization thing comes back.
Then you get interaction-induced localization.
Okay.
And this interplay between interaction and disorder-induced localization is something which is quite interesting. In the case of the many-body localization, right, this is a pretty active field. And as I say, this is a very fundamental field, I would say, because it is very much on the basis of statistical mechanics.
And a second question is, when you discuss the synthetic gauge field, so you said first that the bosons here we are discussing, they are like neutral atoms. But when we introduce the minimal coupling, P minus A, so they are also like minimal coupling also have a QA kind of factor, and that Q is related to the charge of thing.
Sure.
So, but if your particle is neutral, how can it be like coupled to the
because I am extending the idea of, I am just simply saying what would be the equivalent of having a vector potential. Yes, what would be? Yes.
Okay.
So, and then you see that having a phase phi is like having a vector potential in the system.
Oh, okay. So you go opposite way. And then say like T equals to, if it's complex kind of thing, and then we have a vector potential.
Another way of seeing it is that typically in magnetism you do the opposite thing. You have a magnetic field, and then you see that if you have a solenoid, you will have a phase when you go around, which is the Aharonov-Bohm phase. Right?
Right. Yes.
Now here, what you do is to mimic the Aharonov-Bohm phase, and then you say, okay, this is like having an equivalent magnetic field. Right?
Thank you.
Luis, we have a series of questions in the chat box. We'll see. So let me read the first one. What is the physics behind taking the phase stem in a quasi-periodic disordered system?
Sorry, what's more?
So what is the physics behind taking the phase stem in a quasi-periodic disorder system?
You mean this phase?
This I'm not. Mrinal Kanti, can you directly ask this question? Probably that will be much better. Luis, otherwise, can you please look at the chat box also? Just one. There is a.
This can.
Or Mrinal, is Mrinal here?
Well, this phase, if it is this phase, it is just a displacement. Okay. It is just a displacement. This is just a displacement of the overall secondary.
So here's another question related to this. What is the effect of taking random phase in quasi-periodic disorder system for the time-independent and time-varying system?
What do you mean by random?
Yeah, this I don't know. Probably he means by taking the phi to be random, or this is not clear.
Well, this then it will give me something random like this one. The key point is not having the random.
Okay.
Yeah.
So another question is from Sri. Beyond realizing the Hamiltonian, can the system be prepared in some specific initial states, say the ground state or a thermal state?
Yes, this is something that I did not discuss in too much detail, but this is actually a very important point. Both the preparation and the readout of the state. So basically the measurement, because since that around 2010, right, there was a very important development in the experiments in ultracold gases, which is the idea of the quantum gas microscope, which is basically that you can resolve the position of atoms. So you basically take a picture and you can detect the atoms individually in an optical lattice. So you can imagine that the distance between atoms is of the order of, let's say, half a micron or even less, and you can still resolve this position. So basically you can see where the atoms are. So this means that you can measure specifically the positions of where the atoms are, and you can make a very nice statistics because these experiments are very reproducible and so on. Now, you can use this type of techniques also to prepare specific, for example, Fock states in your system. This is the easiest thing to say, to prepare this type of, say, Fock states. And this is particularly important, for example, for the dynamics. For example, you can start with a particular Fock state, right, and study how Fock states evolve. For example, you can prepare a density wave where you have one particle 0, 1, 0, 1, 0, 1, and study, for example, whether the system delocalizes or remains localized. This is what the people has been doing, for example, for many body localization. So you have a lot of possibilities for preparing states. There are other things that I was not discussing, which are other possibilities that you have in this type of systems, which is like, for example, that you can engineer dissipation, for example, in these systems, and you can prepare specific states. Yes. So this is also another possibility which I was not discussing. You can prepare specific states.
Just a comment, actually in Rydberg system, the people are currently doing similar stuff. The crystalline state of Rydberg state. So the second question, for general states, what is typically the time scale till which we can expect the system to reproduce the correct Hamiltonian dynamics?
Well, the unitary dynamics is, of course, from the very beginning, of course, right? But if the question is whether there is some energies, I am not considering that will take, so to say, will become important in the dynamics. Then of course, the question is, what is the energy scale that I am neglecting? For example, when I was deriving the Bose-Haber Hamiltonian, I was neglecting some terms, right? And these terms will, in principle, get an importance in a time scale associated to the inverse of the energy that I am forgetting. But these energies are these time scales are much longer than the time scales of the experiments, because these experiments have typical time scales of the order, say, maximally a second or something like that. After that, the experiment just simply, heats up. Yes, but it's true that there is a given time scale. Yes, yeah. And this is actually somehow not an interesting problem, because, for example, if I want to study thermalization in an equilibration in this type of systems, I may have to wait for a relatively long time. Yes. Yeah.
So, Luis, the last question is kind of technical. So, in the lattice system, say the Hofstadter case, what are the typical system sizes realizable, probably experimentally? Yeah.
I would say something like several tens of sites across in any dimension. I think it depends on the experiments. Now there are experiments which are smaller, but I would say of this order of magnitude. Yes. So these are systems which do not have, like, say, millions of sites, I would say, but well, especially if you go to three-dimensional lattices, you may have actually thousands of sites. But if you have, but I would say tens of sites across in any dimension.
Okay, so that was the questions from the chat box. So is there any?
Hello.
Hello. Yeah.
Yeah. So
I have a quick question. Hello. Yeah. So this kind of synthetic gauge field, can it also be acquired by setting the system into rotation? Because you can create this magnetic field kind of.
Yeah. Yes.
Is that possible?
Yes. Sure. Yes. So actually, for example, in the as I was mentioning, the synthetic gauge fields were first developed in the bulk, so not with a lattice, and there you may induce indeed vortices by doing that, because basically the Lorentz force is the equivalent of the Coriolis force. So basically, you induce vorticity by doing that. Yeah.
Thank you.
There was, I think, another question.
hello.
Yeah.
Yeah. So is there any difference between the supersolids in BEC and the lattice supersolids?
Well, there is an important difference, because if you have a lattice, yes, then you are already breaking some translation invariance in your system, right? So so basically you can get supersolids, like, for example, that, of course, if you should not have the trivial periodicity of the lattice, but you can have, for example, once every 2 lattice sites, for example, things like that. Right? Yeah. This is what is called a lattice supersolid. And this is something which, I must say, has not been observed in the case of polar lattice gases, right? It is something that is supposed that it exists, right? But it's not something that has been observed. As I was saying, in the case of polar lattice gases, there is still a lot of room for studying ground state physics and dynamics. But, for example, one of the things that we have been studying now recently in our group is the fact that if this V here is too strong, right, then the dynamics of this system can be very, very handicapped. So the transport of particles in this substance can be very, very handicapped, even in the absence of disorder. So you get basically many body localization, even in the absence of disorder. And this may actually make very difficult to reach phases in which you need to have very large ratio between this V here, which is the Niels-Nebel interaction, and the hopping. Yes, but you may have actually phases like lattice supersolid crystals, and actually other types of phases, which I was not commenting, for ratios between V and T, which is not so large, and therefore you can still see interesting ground state physics. But still, as I say, this is something that that there is a lot of room for experiments to be done.
Luis, one more question actually, which is related to the previous one probably. So what is the significance of phase difference between the normal and the disordered lattice, included with the quasi-periodic disorder term, like probably the phi itself, that which you are showing.
What is what? Sorry.
So what is the significance of phase included with the quasi-periodic disorder term?
So the quasi-periodic versus disorder, or
AP, can you ask directly this question? So probably he means the significance of phi, or so what is written is what is the significance of phase included with the quasi-periodic disorder term?
This phi is just it's just a shift. I could have removed it. This is not so crucial.
Okay.
Hello, am I audible, sir?
Yeah.
Actually, sir, I want to know when you people are taking the dynamics of the localized system, then they are taking the phase average of 0 to 2 pi of several like 1000 for small system size. Why they are taking this phase average? what is the actual main significance behind this taking phase average, means this phi term?
This phi here.
Right.
This is, I mean, for the case of disorder, through disorder, you should take a lot of realizations, a lot of different realizations in order to have the proper statistics, right? For the case of quasi disorder, the equivalent of taking many realizations is taking many values of this phi. But in this case, you just can take very few of them, and you get still a very good statistics. You don't need to have a lot of phis. Yes.
Okay, means in dynamics, it has not a significant effect on localization, right?
I mean, you see, this phi is just a shift. It's just a shift. It's just where you start. It is important if you have a finite size system, but when your system is bigger and bigger and bigger, it just, what is the meaning? You see my point?
Okay, thank you.
This is where you start to count.
Hello.
Yes.
You mentioned about density dependent gauge. How does it look like in the hopping term?
Oh, the density dependent gauge fields look like this. Let me just write it here. So for example, as I was saying, you can have this type of thing is what you have when you have just the normal vector potential, right? But density dependent gauge field is something like this: EI phi Ni minus Nj, for example.
Okay.
So these kind of things, for example, I mean, we have been studying it in our group, but also other people have been studying it. It has been recently studied experimentally in ETH in Zurich, and this one, basically, for example, you can actually mimic Hubbard Hamiltonians, in which you have, instead of a Bose-Hubbard Hamiltonian or a Fermi Hubbard Hamiltonian, you can have what is called an Anion Hubbard Hamiltonian. An Anion Hubbard Hamiltonian means that your particles under exchange have a fractional statistics. They don't have boson or fermions, but are fractional statistics. This is because you can absorb these phases into the definitions here, and you get something like alpha I dagger alpha j. But the price you have to pay is that the commutation rules between different sites are fractional, not. So this is one of the things that you can do with these density-dependent gauge fields, these Anion Hubbard models, which have a lot of interesting.
Yeah.
So
is there
it
any
can,
other-
one question, yeah. So it can be the Anion Hubbard model, it can be just realized in 2D because, or any dimension it can be realized.
No, unfortunately not.
Okay.
Unfortunately not. This is basically this sort of extended exchange statistics that Haldane, for example, was introducing in 1D.
Okay.
But it cannot be extended, at least not trivially, as far as I can see, to 2D.
Okay.
This will be cool. Yeah.
So any more questions? So if there is no more questions, so this is the final lecture. So I would like to everyone to thank Luis for taking all this initiative and spending his valuable time with us. And it was a great lecture series. I think everybody learned a lot, including myself. So thanks a lot, Luis, for spending this.
Thank you, Rejish.
Yeah.
Thank you.
It was a pleasure. Very nice questions. And I will also pass you the notes of this last lecture. Okay.
Yeah, and we also put these videos in YouTube IISER Pune after some edition and so on. Okay. So there's some. Yeah, okay.
Good.
Okay. Yeah. Bye bye. Ciao.
I will contact you. I will contact you one of these days. Okay.
Okay. Sure.
Okay.
Okay.
Ciao.
Ciao.
Bye.